Hello, Guy Podjarny. How are you?
Hey Simon, I'm good. I'm excited, pumped to get AI Native DevCon underway. So
Absolutely,
very excited for it.
absolutely. So, for those who don't know Guy Podjarny, what can I say about Guy that perhaps won't get me fired?
Yeah, first of all,
So,
you need to start by lowering expectations. Always like great start of it,
okay,
but
let me.
indeed. So I'm Guy Podjarny or Guy Po. I am the founder and CEO of Tessl, and I'm fairly known for founding Snyk before that, and a few other things. And I'm going to give a bit of an intro to AI native software development and how we perceive it.
Wonderful. Well, Guy, without further ado, I'll hand the stage over to you, and I hope everyone enjoys the session.
Sounds good. Well, thanks everybody for tuning in. As I said, I'm really excited for us to kick off AI Native DevCon. We really think of AI's implication on software development implications as massive, and we think it's a group effort, if you will. It's a community activity. We want us all to collaborate and discuss how do we want software development to evolve. And so, really excited. We're going to continue to invest as Tessl in this community and in making it an easy place to share learnings, to share tools and such. I'll talk about that a bit more. I today am going to talk a little bit about how we see AI native software development and a little bit of the journey that we see ahead for community and for Tessl itself. So if you think about software development, software development's journey has always been kind of around making software development easier and therefore more inclusive. We've gone from like punch cards in which it was very much not inclusive. You had to know a lot, but also be willing to invest the time and have access to these machines, into assembly that required sophistication and sort of power and a lot of patience to be able to develop in, but was very powerful. You could do a lot of things. Onto C, C++, easier to build, easier to create, and therefore more developers come into the fold. Many at the time were complaining that you have to go down to assembly if you want to really control it right. And continuing into Java and JavaScript, same narratives. Every time you make it easier to create, and therefore you bring in more people into the fold. And part of the trade-off over here is that you had to give up some amount of control to be able to get that ease of use. So just a few examples here. If you think about C, for instance, this is a little small example that opens up a file and counts the number of lines within it. You have a lot of control in how you're going to do it, but there's a lot of like voodoo words over here that you have to really understand. File pointers and fopen, and you're creating buffers in memory you're going to read stuff into. You have to manage them correctly. So a lot of control, not like much easier than assembly and such before, but a lot of risk is involved as well. If you go to Java, if you see the evolution, it's not less verbose. Java is not known for brevity, shall we say, but you have much easier to understand, like things that are more English language, buffered reader and file reader and read line. It also is a lot safer. It's surrounded. A lot of choices have kind of moved to the system, and they will not allow you to override memory or things like that, and they force you to create exceptions. So safer environment, a little bit less control. That continues into higher level languages and script languages like Python and JavaScript that really start resembling English language. But really, at this point, you really have a lot less control about how things are done. Memory allocation, the choice of file opening, the choice of defaults, a lot of those things go away. But it's a lot easier. It's a lot easier to create. And LLMs really offer us sort of this opportunity to take this to the next level and say, hey, just use English, or actually another language. Just use natural language and say, hey, just print the number of lines in example.txt. And that's amazing. That is very much on the trajectory of software evolution. And we want that, but it's also risky a little bit, because LLMs really make us give up a lot of control, and sometimes maybe too much control. And the question is, can we tap this sort of magic, this power, so we leverage this ease of use, this leverage, this ability to create a lot with few words, but we retain control, right? And we know that when we say print the number of lines in example.txt, it doesn't just print those words, but rather the meaning. We don't have really any measures for that today. To be able to think about how we do that, we have to think a bit about software development from first principles. So let's talk about two things around software development today. One is that code couples today what the application does or software does and how it does it. This is a small example. If you look a little bit at this function that is intentionally not named, maybe take a few seconds, try to think, what is this application doing? You can see the how, you can see the for loop, the counting of it. I won't waste too much of your time. You might have realized during this time that this is a sort function. And it takes an array and it sorts it. And okay, that's all good and well as you do it. But first of all, it's a bit of an indication. So you had to deduce what the application does from the code. And the code also decides both what is being done and how is it done. And we rely on these symbolic, these descriptive traits like the function names and the comments to understand the code and understand what it does. And I think anybody that has a little bit of mileage in software development has already encountered many times cases where that is just absolutely not the case. You see functions that are not correctly named, sometimes hard to name them. You see comments that are missing because there's no functional imperative to actually make those correct. Let's continue this example and think about this function. This is also a sort function. The what of what it does is the same as the previous function. They both sort the array that they get. But this one does it through merge sort. It's a different algorithm. They're both legit. Selection sort is a little simpler to understand and it uses less memory, but it's less efficient, while merge sort is faster, but it does a lot of recursion and a lot of memory. So they're both legit options, but they really demonstrate that there could be multiple hows to the same what. And if you stumble upon this code, you really don't have any indications as to what was the requirement that came in the first place. So you look at this and say, well, someone chose merge sort or chose selection. Why? Was that just a whim of this developer, or was it an intentional choice that met the requirements? If it was intentional and based on the data, is that still relevant? Like, is that still the correct data? Have we gotten more data now? Have we gotten less data? Are multiple people using the same function, multiple functions using this utility function? If you drill a bit deeper, you would notice that if you use sort of string arrays over here, you will get a case-sensitive sort. Is that on purpose, or is that just sort of a bug or an implementation decision that has never been stated? All of those now become a fact of the application. All of that truth sits in the code, and the code ends up describing both the what the application does, how it behaves, and how it is implemented. This led software development to be very code-centric. If you think about software development today, you can say simplistically that it takes some requirements, it goes on to produce some code, then you take that code, you package it up so people can use it, and then hopefully you invest some time in documenting and creating tests on it. I say hopefully because, again, not mandatory. There's no immediate immediate feedback loop, immediate problem that happens if you don't properly document it or don't create tests for it. Over time, the only thing that really kind of truly stands the test of time is the code. The requirements come along, you write the code. The odds of you being able to find those requirements 2 years later are fairly low. 3 years later, 4 years later, the code continues. The code continues and becomes the source of truth of the application. And that's the thing that we decorate. The packages, clearly, it's a built output. We build it, we don't have any precious element to it. And the documentation and the tests, they're partial. They don't represent the application well. The code continues and it gets heavier and heavier over time. Enhancements come along. They expand the code. They add more to it. Bug fixes come along and they add small bits in various places. Edge cases maybe add like ifs and weird things into the code that are not quite elegant, but they address a problem that a customer might have had. Ecosystem changes might really force us to do sort of unnatural things in software upgrades and things like that. All of those make the code messy. The code becomes big. It's hard to hold in your head. We start talking about onboarding developers and how do we kind of make them understand the code to deal with that. We get into refactoring projects that are expensive to it. To make things worse, the docs and the tests, which are not like functionally connected to the code, they're not necessary for the application to work, just for software development to work well in consumption, they fall by the wayside. They get out of date. Over time, changes to the software become risky and we become risk averse. Every time you change, you might have some of that refactoring work on it. You might have more tests. You're trying to judge whether or not changes are worth it. They're worth the risk. And really maintenance of the software for changes that you have to do becomes a big burden. New operating systems, new dependencies, changes to services, you have to do that work. Each one of these changes is risky and expensive. And pretty kind of within a few years, within some amount of time, pretty much every software project gets to the state in which a big chunk of the development team's time is spent on keeping the lights on maintaining the software. The pace reduces for a variety of reasons, including the complexity of the code. This isn't like, I'm not knocking anybody by saying this. This is just the inevitability almost of software development over time. AI dev tools come along, and today they help. They're significant. I'm a big fan of a lot of these AI dev tools. We use a lot of them when we develop software at Tessl and at Snyk, and I highly recommend that you do. But they don't really change any of this broader picture. What they do is they make the lines better. They make the lines faster. It's easier and faster to create code for enhancements, for bug fixes, for edge cases, for migrations. It's also easier to tackle the toil, the docs, the tests. It's easier to maintain those, so they keep those lines straight. But they don't change the fundamental. The only thing that stays is the code, the prompts that created them, all of that user experience, new user experience to create code. That is what it does. You give it language, you interact with it, and it creates more code. In fact, some claim that they create too much code too quickly, and they actually increase the maintenance burden, because many of them are great at creating the code, but they don't actually take responsibility for maintaining it over time. So this is great, but it doesn't solve the problem. And we think we can actually solve the problem, or we can make step change by rethinking the workflow. We think that LLMs allow us to decouple what the application does from how it does it. And this is for a few reasons. First is, the two are more obvious. The first is that it's easier than ever to say what it is that you want. You don't need sort of formal structures and things like that. You can use language, you can use mockups, you can use visuals, you can interact verbally with the system. It's easier than ever to talk to machines, to express what you want. There's a lot of unknowns around it. We'll talk about that in a sec, but it's much easier than before. And that combines with the fact that machines can write code now. And so in the combination of, it's easier for you to say what you want, and the machine is able to write that code, that's a magical combination. And that's what we're seeing also in a lot of these, Claude or ChatGPT, when you go off and you create an application. The third thing that is not really discussed is that LLMs can fill in the gaps. And I think that is a massive unlock and doesn't get enough attention. You can go to the LLM and say, create a tic-tac-toe game without explaining the rules of tic-tac-toe. This is different than what you could do in previous specifications. Up until the LLMs come along, up until this era of AI, every time you wanted software to do something, you had to explain every little bit. And the only places where you didn't have to is places where a problem was entirely solved by something underneath, like memory management in Java. But those were very limited because you confined yourself only to these building blocks that have already been created. In this sort of vast world of human knowledge, you had to specify every time all the different details. And LLMs break that mold. LLMs enable us to say, create a tic-tac-toe game and know the rules. And over time, they can get better at better, or rather platforms that use LLMs can get better at filling in those gaps. If you think about an agency that you work with that has built 5 marketing websites for you, if you come to them and you say, build a 6th one, you need to give them a very small spec, because they know you, they know the domain, they build marketing websites, they do that for a living, they've done it for a long time. So they know what they need to do. You don't need to tell them everything. If this is the first time you work with that agency, you probably need to tell them more. The spec needs to be a bit bigger because they don't know you. If they've never built a marketing website before, you probably need to give them even more specifications. Same goes if you go to some sort of low-cost agency that really, you don't trust as much their execution, you just want the sheer firepower. And the same is true for these LLMs. You can train the LLMs so that they get better at knowing you, at knowing a domain, a type of application. And so they become more like the most senior developer on your team, that you have to give little specification to them to build something versus the most junior one on the team. All of these combine to really say that LLMs make specs practical. They take specs that used to be kind of very poorly structured, hard to build, overly detailed, and limited in what they could create to building blocks that have been pre-imagined, to something that is flexible, that can fill in the gaps. And we think that is massively powerful. And it allows us to think of a transition from code-centric software development to spec-centric software development. And so instead of accruing the changes over time to the code, instead of enhancements and bug fixes and edge cases, ecosystem changes, all of those accruing to the code, to the implementation, those changes accrue to the requirements. And the requirements represent what the system does over time. To strengthen that, you also pair up the requirement with the tests, and you put all of those in this specification. So the spec now says what the system does and has some examples, some assurances, a lot to say about that. that help verify that the software indeed does as it should. Only to the degree that you care about. You might want a button, you might not care about its color. So it would verify to the level that the spec cares. Not only would it generate the code, this approach also allows all of these ancillary objects, these descriptive objects, to actually become generated objects. Documentation, software bill of materials, all sorts of attestations about what has occurred, mocks, API documentations, all of those can stay up to speed because they become a part of the software, always verified, always vetted against that spec. We call this sort of new paradigm of spec-centric development AI native software development. And we think it is very powerful. We think there's there are many advantages that this can bring. Let's talk about a few of the key ones. The first one is that you always know what the software does. This is kind of in the name of spec-centric development. When you think about code-centric, you're going to come along, as we just discussed, you might change something. You might go from the merge sort to the quick sort, and you might change the color of a button. And in the process of that, you might be changing what the application does, even without intending to do so. And that is just by the nature of the beast, because there's actually no place for you to update except maybe these ancillary docs that are not functional to say what is it that you have changed. And so it's very likely that you break that. In the spec-centric mode, every change that you make, every pathway that might modify the code, first vets that the spec continues to be adhered to. And so at any time that the spec is always systematically applied to the code. You know what the system does. A closely related behavior is that software becomes less fragile. So in the code world, in the code-centric world, today's reality, every time you add a feature, you might break another. Let's assume you do test the new feature to make sure that it works, but when you add that feature, you touch code, you modify code, and you're really dependent on these, again, rarely comprehensive tests to know that you haven't broken anything else. And so this is just kind of the reality of software development today. You may, and you often do, break other functionality. In the spec-centric world, you define the change that you want to the functionality of the app in the very document that has all the other functionality in it. And so, first of all, even visibly, you can see whether there are implications. And when the code gets generated, every time it gets vetted against the entirety of the specification. And so you always know what the application does, and you are far less likely, in fact, in the system you, in theory, would never, in practice, there's always edge cases, break the application. So you always know what the application does, and that allows you to make changes faster. It allows you to have more confidence in trying things out versus that fearful state that you were before. Let's take it a step further. Like, both of those are really like the concepts of spec-centric development, and so obvious advantages. Let's talk about what are the downstream implications of that. When code started getting popular, new compilers eventually allowed the same code to run on multiple platforms, multiple architectures. And this was a big unlock and a big advantage over assembly, and really kind of felt magical at the time because you can have code that is portable. Spec-centric development takes it to the next level and actually takes these specs and is able to generate software for them across languages, across stacks. You want your JavaScript version, your Python version, no problem. You want this on iPhone, you want this on Android, that's fine. All of those do depend on some proficiency of the system to support each one of these ecosystems, but the definition of your functionality is very much in the specification, in the validations, and therefore things become portable. This is interesting. It starts saying, okay, what would you do with sort of language agnostic software? How do we think about that? But it is also, again, very, very flexible and adaptable, because you can use now the software to run more sort of a secure barebone Rust environments versus more web-based JavaScript and more. You can append to that your own context. And so the generation itself, it takes that specification, but it also takes in the context that you provide to the system about your preferences, your environments. This is really where getting to know you, the equivalence of that I mentioned before, comes into play. But it also includes, how is it that you want to describe your system? Are you budget constrained? Are you do you have your own interpretations or patterns of how you want code built because of a variety of trade-offs? All of those get packaged into the context, which can really become quite elaborate. And together they feed into the code generation, and you create that code. And so it really creates this adaptable software that can adapt itself to your needs, whether it is a well-known stack or it is something that is specific to you. Adaptable software also offers what might be the biggest advantage of AI native software development, which is autonomous maintenance. Software is always produced from that combination of the specification and the context that you want to generate it in. And maintenance, by definition, is change the code without changing the spec. I want you to modify it so it works on this new operating system, on this new dependency, upgrade this secondary thing, or use this new service, but make the application work as it did before. Because the code is always generated from those two, when a change like that occurs, as long as the platform is aware of the context changing, all you do is you take that change, you create a new context, and you create the code. And the code always is vetted to the spec. And therefore, you have assurance that these maintenance tasks do not break the application. And in the edge cases in which they cannot be done, it surfaces it to the user, but it doesn't surprise you. And so autonomous maintenance is a huge benefit because vast majority of these changes, they're not hard changes. They just require that assurance, that sort of testability, verifiability of the environment, and that ability to describe the change in the context. And by freeing up maintenance, by removing this maintenance burden, you really offload a lot of effort from software. And you allow existing software that just continues to run to do so without effort. And you allow developers in live systems to spend their time creating and innovating. A closely kind of approximate to that, if we continue down that sort of journey of what could you do if you could verify the functionality, is you can create better software through automated optimizations. So you can take that code and you can add agents that make it faster, that make it more secure, that make it more accessible. These also benefit from LLMs. They also benefit from the sort of power of look at the code and make it better. And you'll hear some of that in some of the talks today. But they are today hard to trust because they're unpredictable. You lose too much control. They might break your application. And this ability to verify them to the spec opens up this opportunity to say, attach this sequence of improvements to my code and just make it better, always verifying it to the spec. As a result of that, you can create software that is just dramatically better. Imagine an agent that every time a vulnerability comes along, it identifies it, it fixes it, and it makes sure the software didn't break. That catches up to all the compliance issues that you need to address to and make sure the code is modified for that, to make sure that looks for optimization opportunities and also even is aware of new optimization techniques for different browsers and creates that. A lot of opportunity to make software better with a lot less effort. So this opportunity to optimize doesn't end in the build process of it. It also happens post-deployment, and it can create self-optimizing software. You can take your code that has been created from the spec, you can deploy it, you can have telemetry. And today we look at this telemetry and we try to learn from it so we can improve and evolve our software. But once again, that's a very expensive process and the changes are risky. So we don't do that much. I'm starting to sound like a broken record here, but the spec-centricity can help you change that. You can take that data, learn something about the system, see a bottleneck of performance, for instance, try to optimize it, create better code that addresses that bottleneck, verify to the spec, and deploy it. This process creates this self-optimizing software that after it runs, it just harnesses itself. It's the same concept of what we do today, which is mature software gets better, but in a much more automated, granular, and faster fashion. And this continues to sort of similar concepts like dynamic software. You can create versions of the software that are cheap at night and fast during the day. And even personalized software that optimizes itself to the user's specific needs or to a specific environment to it. All are continuations of this adaptable software. So these are just many of the capabilities that we can build that really kind of tap into the power of LLMs and AI, thanks to this sort of spec-centricity that in turn is unlocked by the power of AI. And at the end of all of this journey, we continue to go back to that sort of core expectation and opportunity to make software development and software creation more inclusive, much more inclusive, because indeed we level it up to the sort of ease of creation of language. So to summarize, we think AI native development allows us to unlock this like maximum leverage, maximum ease of creation with a little bit of a few words, create something big, but gives us the strong controls that we need to be able to tap into that power. And this combination is really what we need to be able to rethink software development and make it 100 times better versus continuing to drag along a bunch of the problems that we're encountering in software development today and try to kind of patch on top of them. So this might sound somewhat idealistic, and you know, to an extent it slightly is. There's a lot here, and there's a lot to still build. So let's talk, you know, about a few of many open questions that are here. The first one that might be obvious is, what is this magical spec that you're talking about, and how would you validate it? Those are good questions. We have some theoretical answers to them, and we're working on that at Tessl. But we think fundamentally there will be many ways to specify software, and there will be multiple ways to validate it. The way that you would define a mobile game is not the same that you would, the way that you would specify a mobile game is not the same way that you would specify a pacemaker or a marketing website. Those require different emphasis. The way you would validate those types of software is also similarly different, right? You might need a deployed environment. Think about infrastructure as code. How would you validate that? So we think these are ecosystem plays, and they come back to why we think this is something that is broader in a community play. There's also questions around how do we deal with that software when it misbehaves? The first one is, how do you debug or observe in runtime this type of system? If you didn't write the code, what do you deal with? This is not that dissimilar to what we've seen with assembly or with sort of Java bytecode, but it's still a problem that we have to tackle. Say, how do you understand that there's a problem? How do you get to the root of it? How do you know how to fix it? And how do you observe a running system at this higher level of spec? Closely related to that is, a lot of the power over here comes from this delegation of decisions to the LLM. For instance, the tic-tac-toe rules. How do you know that it got the tic-tac-toe rules correctly? How do you know if it picked merge sort or quicksort? When do you care and when do you not care? How do you control those degrees of freedom? So we need new methodologies around how do we engage with the LLM's decision in a way that is reasonable, that is not just a magical black box that we're just hoping. That's not good enough controls, but that allows us to interact with the system and override decisions when we need and promote them to the spec in other cases. You go on to deployment and you think about how do you even version and package these types of adaptable software if they become more dynamic. This is similar to machines in the data center versus elastic computer in the cloud. And probably the biggest question of all is, like, what is the role of an AI native developer here? We think of this as a software creation craft. We think you're going to get better at it over time. We think you have a lot to kind of contribute here. And generally, most of the skills around software development are still very applicable here. Systems thinking, understanding of the user needs and reducing that into what is the solution involved of it, a variety of forward-looking trade-offs. All of those are still very much needed. And the best developers today are not deemed the best developers because they're the best coders. It's about that combination of skills. But still, we need to define what is this AI native developer? How is it different? We think people will evolve up the architect or product manager routes a bit more, use those skills more. We need to define those. These reasons and more are the reason we think of AI native development as a new paradigm. We think of it as a change in software development. It's like DevOps. It's like web development. It is not a product. It is not a platform. It is a paradigm. It's a new set of best practices. And the reason that we think this is a community exercise. And therefore, in my kind of last slide here, I want to use that as a call to action for everybody around. Whenever a new technology paradigm comes along, it kind of rocks the boat. The web or mobile or even the personal computer, and now with AI, it's messy. It's hard to understand it. It's different than a bunch of things that we work with, and it's easier to kind of grok it, to absorb it in an opinionated, closed environment. This is the system here. It's working in a more narrow fashion, and so it's easier to accept this messy new AI tenant in it. And understand it within those confines. But we think that really doesn't allow AI to live up to its full potential, and that it's actually like a pretty sad reality for software development if it remains closed, if the future is you work with one of these 2, 3, 4 dominant platforms, and that's the only way you develop software to an extent like we see in mobile. We think the future of software development should be open and composable, that many exciting tool builders can create pieces of software for different stacks, for different scenarios, that can specialize and evolve and out-innovate and create new capabilities, and that those building software can compose those solutions into their environments. We think that's how AI native development should form. And so we're investing, as we said at the beginning, in AI native developer community, in this, trying to create a space in which we can also talk about this, express opinions. We invite, whether you're sort of building tools or you're experimenting with those tools and you want to share your learnings, or you just have opinions about this domain, come join the conversation here, share what it is that you've learned, what are your views, what is the new thing that you're proposing on it, and collaborate together to form this view, this AI native software development paradigm. So that's it for me. I hope you're as excited about AI native development as I am. I think there's huge potential here, and I'm excited to work with all of you in sort of shaping the future of software development. Thank you.